I do with kids.
Yeah. Hey guys, this is the
Welcome back.
Yeah.
Today we're going to do a little more
Hey guys, hey bad science. Like, I'm back now.
This is where I do. Jorge,
Yes.
I do physics early because the schedule looks like this.
Word myself. At least you're treating yourself, right?
Yeah.
That's good too. That's
Red essay tries to cry on the paper. Reward myself with Netflix for all my hard work.
prior.
Now it's just fun.
The differential equations you get.
In this?
See you tomorrow.
Morning. Okay, so no announcements. We're going to jump straight back into our exploration of rotation. Just remind you where we left off last time. Kind of preliminaries on kinematics. Maybe I'll put this over here. We're not really going to touch on it. That's pretty much where we left off last time. We had fairly concisely introduced the rotational analog of the variables we'd introduced with linear motion. So angular displacement, angular velocity, angular acceleration, the usual definitions, and then pretty much without any derivation. It's not a good use of our last time, but it's the same format of derivation that we use for linear variables. We come up with the equations of motion for constant angular acceleration situations, okay? So that's where we left off last time. You'll be getting a little bit of practice with this stuff this week, obviously, on homework, and a little bit in recitation and tomorrow. But I'm assuming for the most part, you're going to find that relatively straightforward. Same idea, same problem-solving strategies we had a month ago for linear motions. It's just getting used to rotational variables and a sort of rotational mindset. The only thing to be aware of is, as it was back then, the importance of keeping signs directly taken account of. All right, so we're going to move along right away from that and introduce the topics that are up on the right-hand board. First thing we'll do is a little bit new, but straightforward, which is to look at the relationship between angular quantities and what I'm going to describe as their associated linear quantities, and that'll make it very clear in just a moment. Then we're going to go a little bit out of order compared to what we did for linear motion and introduce already now, before even we've talked about dynamics for rotation, we're going to introduce the kinetic energy for rotation. And the reason for doing that is it turns out we need to have a somewhat different concept of what I'm going to describe is the equivalent for mass. So obviously we have mass when we talk about linear motions, and that factors into Newton's equations. But it turns out, and a good way of introducing this is through the idea of kinetic energy, you need to have a modified concept for the analogous situation for rotations. And what we end up with very quickly is the idea of something called rotational inertia, or some of you may have learned this is the so-called moment of inertia, which takes the place of mass in rotational situations. And it's a little bit more complicated. It has to do with where the mass is distributed. But once we've determined it, once we've defined it, it takes the same role that mass took in the linear situation. So that's why kinetic energy comes in a little bit early. And we'll spend probably a fair amount of time talking about this rotational inertia. Hopefully we'll do a couple of sample problems on that, and you'll certainly have one recitation this week. And that will lead us at that point to having pretty much all the tools we need to turn over to dynamics, which is to say forces associated with rotation. And all being well, we'll get on to an initial discussion of that in the formal talk just before we wrap up this morning. So that's the roadmap for today. All right, so let me talk first off about the relationship between angular and linear variables. So relating angular or rotational, I'll obviously use those two words interchangeably. So relating angular and linear variables. Okay, so some random shaped object. I'll illustrate this in just a moment with our bicycle wheel. We may be talking about some random shaped object that is rotating about an axis that is pinned at that point. Okay? So the perspective I want you to be thinking about with this is probably a three-dimensional object, but we can look at this two-dimensional shadow for now. There's an axis of rotation that is into or out of the plane of the chalkboard, and this thing is rotating about that axis. Okay, so spinning, if you will, rotating. And what our brief exploration of the relationship between angular and linear variables is going to be asking and then answering is, if I take some point on a rotating object, maybe it's this point P, and remember this thing is spinning about that fixed axis here, so this point P is also spinning about that fixed point. The question will be, what is the relationship between the instantaneous angular variables, the ones that I have on the chalkboard on the left, and the associated linear variables? So what do I mean by linear variables? Well, I might be interested in, aside from the, let's say, the angular displacement this goes through in a certain time interval, or its instantaneous angular velocity, I might also be interested in knowing something about the sort of arc length traversed here. But I also might be interested in knowing what is the instantaneous velocity at this point. And if I was to fold in acceleration here, I might be asking the question, what is the instantaneous acceleration of this point? Okay? So I didn't really draw this in a very compelling way, but hopefully in a moment you'll see more carefully what I mean by this. So, first off, let me take you back to something we already know from when we first explored circular motion. And it's the following relationship, which allows us to, let me write this in terms of these variables. It allows us to relate the angle subtended in a certain rotation. And I've already been fairly lazy in my notation here. Instead of putting delta theta, which would be more correct, I'm dropping the delta and just calling this a subtended angle theta. So we can relate this to the radius of whatever it is that's moving in a circle. Let's call it r. Is our angle theta. And we can relate the subtended arc length to those two variables by that relationship. S equals r theta, with the caveat that theta is in radians, because in a sense that's built into how we actually define this relationship here. Okay? So, a little bit of a slightly, what's the word I'm looking for here, slightly dubious definition of the word linear, but let's see how this works. So, subtended angle theta, obviously an angular quantity with define this as an angular displacement. This is an arc length, but nevertheless it's a line. So in that sense, we're going to claim it's linear. Okay? That's the bit that you may be a little uncomfortable with because it's not a straight line, but at least it's a line segment. So in a sense, this is a relationship between a linear quantity and an angular quantity. Okay? So we're going to take this and simply differentiate it once and then a second time, and it's going to allow us immediately to get relationships between linear velocity and angular velocity, and then between linear acceleration and angular acceleration. So let's differentiate this with respect to time. So let's differentiate with respect to time. So if I take that relationship and simply differentiate it with respect to time, what am I going to get? Yeah.
Like ds over dt, which
Okay.
is instantaneous velocity,
Okay.
I guess. And
Yep.
then,
Keep going.
you're gonna get d theta over dt.
Okay. And I notice you missed something else.
No.
Want to explain to us why?
Because you're differentiating, so the constant goes away. I guess.
Does it go away in this case? It's just a multiplier. Yeah.
This remains, and then you get d theta dt.
Okay.
You get r theta t, which is equal to our angular velocity.
Right. So this is a multiplicative constant. It is a constant. The radius of whatever this thing is at is presumably fixed if you have a rigid object. So this is a constant, but it doesn't go away if it's a multiplier. Okay. So yes, ds by dt equals r d theta by dt, or in language a little more concise, v equals r omega. So this is our definition of angular velocity. So angle subtended over time taken. Okay, so by straightforward differentiation, we find this. Now I just want to make one comment about what this is. So the angular velocity we already defined last time, it's pretty straightforward. This, however, is the instantaneous velocity at the point P. And presumably it's tangent to the circle that this point is mapping out as it rotates. Or another way of saying this is that it's perpendicular to the radius. Now you know that to be true, okay? Something that's moving around in a circle of radius r, its instantaneous velocity is always perpendicular to the radius, always tangential to the circle. Nevertheless, this is pretty straightforward, all right? So now the instantaneous linear velocity is r times the instantaneous angular velocity. So again, linear and angular, we get this relationship. We're going to do this one more time. Same idea. I don't think I'll even write out the intermediate step. So differentiate with respect to the line again. And maybe I'll simply ask you, what is the resulting expression we expect in this case? So maybe forget about this intermediate step, or at least don't get it in your mind. And tell me what would be the expression we expect to get out at the end of this second differentiation. Yeah.
A is equal to alpha r.
A equals, I'm going to recast it like this. Alpha r, r alpha, same thing. Okay, multiplicative constant with r, and we end up now with an angular acceleration, alpha, and an linear acceleration. Okay, good. All right, two things I need to talk about. First off, these quantities are, in a sense, always tangential. So, tangent, this is tangent, and this is tangent, meaning it's always perpendicular to the radius vector. So, hopefully that's clear. So that's one thing. And the second thing is in particular of importance maybe in this case, but I'm going to start off with this. If I have no so in fact, if there's no angular acceleration, this comes back to our uniform circular motion idea that we introduced a month ago. Notice there are no vectors in here, so this is continually changing vector, but the speed is constant. So this is uniform circular motion if there's no angular acceleration. The one that I most want you to draw your attention to is this, because now we have a tangential acceleration vector. Maybe I should go back onto here and quickly draw it. So I can highlight this, but let me now say that I've got a tangential acceleration vector, which again is tangential, perpendicular to the radius. What other kind of angular, or what other kind of acceleration do we know is at work if I've got something that's moving around in a circle? Yeah. Okay. So, and we also have a centripetal. Okay, just reminding ourselves of what this was back from a few weeks ago. Okay, so let me just focus on these two aspects of acceleration now for rotational motion. So if I'm moving around in a circle, this is always present. Okay? So if I'm moving, this is non-zero. I always have centripetal acceleration. So pointing towards the center of the circle. Always there. This one is only here if I have a change in sort of angular motion, angular acceleration. So of course, if this is zero, the case we just talked about, this is zero. Okay, so we'll make sure that's clear. So this only holds if I have angular acceleration, which means the speed in terms of its magnitude is changing. Okay, and then I have this tangential component. So let me just write this in red because it's kind of important. This is always present, assuming it's moving. And this is present only if the angular acceleration is non-zero. Okay? So let's just pause there and make sure you're absorbing that. I know it's sort of two fairly simple statements, but it actually gives rise to confusion more often than you might expect. Questions on this? I'm just going to make some comment about the resulting acceleration vector. We're good? Okay. So in the case where we have both of these, so first off that means we're moving in a circle, but it also means we're moving around in a circle with changing speed. Then apparently we have a net acceleration, which is a combination of these two things. Okay? So let me just make sure again that this is clear. This thing is rotating, and apparently there's angular acceleration, alpha. And so in terms of the two components of the acceleration that we know must be present, there's the centripetal acceleration pointing towards the center, and there's the tangential acceleration pointing perpendicular to the radius towards the center, or if you like, tangential. So the resultant acceleration is the sum, vector sum of these two guys. Okay? So again, this gives rise to confusion more often than you might expect. But in this case, that is the resultant acceleration. As it must be, it's the vector sum of two acceleration components. Okay? Questions, comments?
What's the resultant acceleration?
So the question was, what's the resultant acceleration relevant for? Good question, because more often than not, it's useful for us to work solely with its components, centripetal and tangential. Of course, accelerations we know are related to forces, and the rotational analog of forces that we'll introduce hopefully here in this class. So in that sense, we would certainly be able to relate it to something to do with forces and dynamics. But in exactly how we're going to do that, I'm going to hold off on explaining a little bit. But I like your question. practically speaking, more often than not, it's the components that are useful to work with. Yeah.
What's the acceleration in the middle?
What's the acceleration
Like
in the middle?
the label on the
This one or this
yeah,
one?
that one.
That one? Yeah, apologies, kind of small. RES or resultant. So centripetal, tangential, RES for resultant. Yeah.
So do we see that the point is only because like it accelerates only as a result of direction?
Yeah, effectively, in the case that both of these are present, yeah. But again, we more often find it convenient to kind of break it down into the perpendicular and radial components. But yes, that's exactly what is the case. Okay. All right. So let's see if this makes any intuitive sense. I'm just going to go back to the velocity case and look at this. So we use spinning bicycle wheels quite a lot for obvious reasons. So now I've set this thing spinning about a fixed axis, so it doesn't look like it from where you guys are. So the fixed axis, and now if I look, for example, at the second expression, the relationship between instantaneous linear velocity and angular velocity. Okay, so I set this thing spinning at a certain speed, so it has constant angular velocity. But if I look at points at varying radial distances from the center, what can you tell me by simply looking at the expression on the chalkboard? What can you tell me about the radial speed as I go out from the center? So the not the radial speed, the tangential speed, the linear speed. What can you tell me about the linear speed as I go out an increasing distance r from the center? Yeah?
It increases.
Sure increases, and it increases linearly with distance, right? So if I'm here, if I go all the way out, I've got a certain instantaneous tangential or linear speed. Halfway towards that, it's presumably half the that value of the linear or tangential speed. Okay, so it just goes in proportion to the radius away from the axis of rotation. So you have plenty of examples of that, but the sort of classic one that's often used to really drive this home. Not something perhaps many of you have experienced at firsthand. Maybe you haven't even seen it. It used to be a kind of classic thing on TV in the old days when entertainment was simpler than it is today. And the classic example is taking a line of people who are on an ice rink, and they're lined up in such a way that there's a person who's going to be at the center of a spinning group of people. A line, half of them facing that way, half of them facing this way, and then they start kind of going around. And what you see, of course, is that if it's moving at constant angular velocity, well, what does that mean? If I start off with a line of people pinned at the center, and they're moving at constant angular velocity, that just means they must be staying in a straight line, okay, as they move around that central axis point. But of course, the people who are further out are moving way faster than the people who are closer to the center. And so this becomes pretty dramatic when you have these extended lines of people spinning about a fixed point on an ice rink, because the people at the far end are having to move incredibly fast just to keep up with the same angular velocity that everyone must have. So that's a kind of classic case of how the tangential velocity increases linearly with distance from the axis of rotation. So this relationship. Okay. All right, so that's pretty much all we need for now in terms of the relationship between tangential, aka linear variables, and their rotational kind of counterparts. All good? Okay. So I'm going to turn our attention immediately then to this idea of kinetic energy. A little bit out of order compared to what we did with linear motions, but the reasons for that will become immediately apparent. So, kinetic energy of rotation. And of course, since things are moving, there must be kinetic energy. It's simply a question of how we define it. So we're going to imagine an assembly of discrete particles. So we'll take an assembly of discrete masses. These labeled by letters of the alphabet. expect to from what we know already. And then we'll see how we can manipulate this to learn something a little bit new. So our usual expression to determine the total kinetic energy for this assembly of objects that's rotating. Okay. All right, so now I'm going to make use of the fact that we know something about the relationship between the tangential linear velocity and the angular velocity. So we know that V equals R omega. So all I'm going to do is make use of that and substitute for V the relevant expressions for each of these masses. So let me do that. So now we have half ma. So now I have R omega A. We do this explicitly like this. Plus 1/2 mv times RB omega B squared. Space for the rest doesn't matter. So I've got a simple substitution for the linear velocity, replacing it with R times the associated angular velocity. All right, but it's rigid. So an object being rigid means its shape doesn't change. So if its shape doesn't change, what does that tell you about the angular velocities of all of the objects that make it up? Let's get some. Yeah.
They're all equal.
Yeah. So that's an important thing to think about. And again, first time you see it may require a moment's thought, but as soon as you see it after today, hopefully it'll be kind of clear. So it means that all of the angular velocities are the same. Let's just call it omega. So we're no longer distinguishing this by the angular velocity of each individual mass. They're all sharing the same rotational motion. That's the only way they can stay in the same shape when we're talking about a rigid object. So if that's true, I'm simply going to take advantage of that, and it tells me now that I can write this as K equals 1/2 omega squared, and then what am I left with? MA RA squared plus MB RB squared plus MC RC squared, plus so on and so forth. So now I've slightly manipulated this, taking advantage of the fact that I know it's a rigid object. And it's that combination of variables that is now inside those parentheses that I'm going to kind of define as being a new parameter. So let's take a look at this. It's kind of defined for us once we know what our object is, right? We've got certain masses at certain positions. Certain masses at certain positions. So again, this is a rigid object. This is a fixed quantity for that object. And so it turns out this is a sufficiently useful variable that we give it a new name, and this is the rotational inertia. So this is rotational inertia. It's given the symbol capital I by convention. So now we can define this. We'll write out rotational inertia again. It takes a little bit of time. But it's basically the sum for discrete masses of mi Ri squared. Okay? So I'm simply taking that and summing over all of my constituent objects. And that's essentially the rotational inertia. Now, if I do this, I can simplify my expression for K. Now looks like 1/2 I omega squared. So, this is a sort of next example of where